Welcome to this session on computational thinking. In this session, we're going to look at the term computational thinking. We're going to define what it means and how it can be applied to solve problems in today's world. And more importantly, how it can be applied to program computers to solve problems. So, what is computational thinking? Well, computational thinking is an approach. It's a way of solving problems, of thinking about problems. It's a toolkit which can be used to solve problems and be used to program computers to solve problems. So that sounds like a mouthful. So what does that mean? It's a way of solving problems, a toolkit that can be used to solve problems. Okay, let's have a look. So when you've got a problem, instinctively we use our experience and skill sets and skills to solve the problem. But what if there was a way, a model to approach how to solve problems? A logical approach that can be applied to programming computers to solve those same problems, well-known problems of today, and the problems that are not yet known for tomorrow. So let's approach this by looking at the different methods or approaches to solving problems in the computational thinking model. So there are several methods or elements of the computational thinking model. And one of them is decomposition, another is abstraction, another is pattern identification, another is algorithms. So let's take a look at how these can be applied to resolve problems and support the computational thinking. Well, decomposition just means breaking down a large problem. So we're taking a very large problem and breaking it down into smaller parts. Okay, into smaller parts. So a problem that might be very large and unwieldy to resolve, if it's broken down, and then you solve the smaller parts, and then through the resolution of the smaller parts, you're then able to solve the larger unwieldy problem. So that's decomposition. How about patterns? Well, pattern identification is all about identifying patterns. So we're identifying patterns so that we can make predictions. To make predictions. A bit like what weathermen do. So weathermen have studied patterns in weather. And because they've studied those patterns, they can now make predictions of future weather, make future weather forecasts. And therefore, we can resolve the problem of, okay, we have to do X, Y, Z next week. But will we have the weather to do X, Y, Z next week? And weathermen are then able to look at patterns and identify patterns in historical weather patterns, and they're able to therefore make predictions on future weather based on current patterns that they see and identify. Abstraction. Now, abstraction is an interesting one because abstraction is about focusing on details. Now, specifically focusing on details that we need to solve a specific or particular problem. So it's focusing on details that we need to resolve a problem. Okay? Now, that also requires us to ignore details that we don't need to resolve a problem. So for example, you have a map of the city, but I'm only going I'm going from A to B, and so I'm going to focus in on the route, on the details I need to go from A to B, and then I'm going to ignore everything else on that map that I don't need, that will not help me reach my destination. So abstraction is about focusing on details that we need to resolve a problem. Algorithms. Well, algorithms can be defined as a step-by-step set of rules that resolve a problem. Step-by-step set of rules that resolve a problem. It can also be thought of as a sequence of instructions that resolve a problem, or both. Step-by-step set of rules and a sequence of instructions that resolve a problem. Okay, great. So we've spoken about 4 elements of computational thinking. Okay, how can we apply them to help us solve problems? Okay, let's have a look. So if we go, I'll just clear this. So if we then say we got a problem here, I'm sure a lot of people recognize this problem. So this is a problem where the farmer crossing the river problem. So we've got a farmer here. Okay, he has a fox, a rabbit, and cabbage, and he's got to get across the river. But here's the dilemma: he can only take one item across the river at a time. Now, if he takes the fox, by the time he returns for the rabbit, the cabbage will have been eaten by the rabbit. If he takes the rabbit, if he takes the cabbage, by the time he returns, the fox will have eaten the rabbit. So he's got a bit of a dilemma here. If he takes the rabbit and then comes back and takes the fox, by the time he returns with the cabbage, the fox will have eaten the rabbit on the other side. So what are the step-by-step set of instructions or rules that can be provided to the farmer to resolve this problem of getting across all these items to the other side of the river? Okay, now at this point, we can go away and have a think, but I've already got an exemplar solution, so we can look at that. So here we go. Farmer takes over rabbit, returns empty, takes over cabbage, returns with rabbit, takes over fox, returns empty, takes over rabbit. And there we go. These are the rules, or step-by-step set of instructions, okay, a sequence of instructions to resolve the farmer's problem. Okay, so we've just applied one of the elements, algorithms, okay, an algorithm to the farmer crossing the river problem. Okay, what other ways could we apply the elements of computational thinking to resolve the problem? Well, we can use these elements to play a game, or specifically program a computer to play a game. So that's interesting. How can computational thinking be used to program computers to play a game? Okay, let's think about the game called Guess My Teacher's Number. Okay, so in this game, you have to guess your teacher's number. So given that your teacher tells you that his or her number is between 1 and 10. So this is the range, okay? The range that you have to guess from. So we can then apply rules to playing the game. a range has been provided. What is one rule? Okay, so we've just applied rules. Okay, rules, an algorithm. Okay, so rules number one, the range is you must be given a range. Rule number two is that to guess the number, you can only ask binary yes or no questions. Okay, so that's rule number two. Okay, great. So how can that be applied? Well, rather than just say, is your number 5? And a more sophisticated question could be, is the number 5, is it a number that's 5 or greater? Okay, so now asking that question provides you or allows you to use another or apply another element of computational thinking. Okay, so if the answer is no, my number is not 5 or the number 5 or greater, then you can apply abstraction. Okay, you can apply abstraction to resolve your problem. So you could then say, okay, fine. So I know that all numbers between 5 and 10, I can ignore all numbers between 5 and 10 and focus on all numbers between 1 and 4. And then you can apply the algorithm, the rule, yes or no question to the range between 1 and 4. And if you get that wrong, you can then apply abstraction again to reduce the range until you get the right answer. So here so in this game we've applied algorithms, an algorithm to set the rules of the game, and we've applied an abstraction to support the playing of the game. So let's bring all this together. Computational thinking is a way of thinking about and it's an approach to solve problems. Okay, and you apply the different elements of computational thinking, which there are many. We've talked about 4 today, one being algorithms, another being decomposition, another being pattern identification, and we've shown how we can apply those elements to solving problems, and how computers can be programmed to solve current and future problems with those elements. Okay, so that about wraps our session on computational thinking, and I hope at the end of this session you've got a better idea of what this concept means and how it can be used. Thank you.